Welcome back. We're going to start a new chapter, chapter 13. This is a chapter that talks about recursion, a very mathematical way of thinking and also a mathematical way of programming. This is going to take a little bit of a departure from our learning so far, in which we've been talking about data types and then data structures. We're going to get in the middle here briefly and talk about recursion, and then we're going to go back to our discussion of data types before moving on to our drone project. So recursion, we've seen it in CS10. Let's review a little bit what it looks like when we do it in Java. Move right. Our goals for this chapter are to be able to practice, we've learned a little bit in previous courses, but to practice thinking recursively, to learn about recursive helper methods, to understand the relationship between recursion, which is one way of solving a problem, and iteration, a fancy word for loops, which is another way of solving a problem. And we want to also understand when to use a recursion and how that affects the efficiency of a particular algorithm that we might want to implement. We also want to analyze a few problems that are much easier to solve by recursion than by iteration. And also how to process data with recursive structures that use mutual recursion, which is where you don't just have one method calling itself, but you have a loop of methods calling themselves. Move right. Let's set ourselves up for understanding recursion by looking at a simple problem called the triangle problem. We're trying to calculate triangle numbers. Generally, when we talk about recursion, what we're using this idea of making one method that gets called over and over and over again with subtly different parameters being passed each time, so that as a chain of these calls are made, we build up an answer to a problem that we care about. So if you think about a motivating example of maybe a Mayan temple that's constructed of a bunch of cubes of stone that are stacked on top of each other in a very structured way, we might want to ask the question, what's the volume of that? What's the volume of that Mayan temple? And we can do that using a recursive algorithm. Rather than looking at it in the three-dimensional case, which we did with some JMonkey engine earlier, what I want to do this time is just think about a very simple version of this, and it's going to be a two-dimensional version. And what we're going to try and do is we're going to try and calculate the area, because it's two-dimensional, of a triangle that has a particular width. And we'll call that base width n, because we're going to figure out what the width is no matter what n the user of our class calls us with. When we draw it, we can draw it with some square brackets if we want, just to visualize what's happening. And when we draw it that way, we can imagine that a pair of square brackets has an area of 1. So that's like a Mayan temple that just has one block, or a triangle that just has one point on it. If we want to find something called the nth triangle number, then we need to add up all the blocks that are associated with that size triangle. So for example, the third triangle number is a triangle that has a base of 3 and then proceeds up one at a time, subtracting one block as we go up the layers, a layer of 3, a layer of 2, a layer of 1, and the answer to the question, what is the third triangle number, is 6, because the total number of blocks that make up a triangle structured this way is 6. Small numbers, it's easy to compute, but as we think about larger numbers, it gets a little bit more complicated. Move right. Using Java's object-oriented structure, we can design a solution to this problem in a particular way. It's not the only way to design it, not the only way to solve this problem even, but here's one particular way. What we'll do is we'll design a class called capital T triangle. And when we initialize that, when a user of our class calls the constructor, they'll call that constructor with the base width of our triangle, so whatever's at the bottom. So for example, if we wanted to try and solve the problem from the previous slide using this class, we would call new triangle 3. And then the constructor would get called. We would store the number 3 in our private instance variable width. And then there are other methods that we use in this class as well. But that's just the constructor. When we call it, we construct it with a particular width. Move right. The easiest case to solve is when we have a triangle whose base is a width of 1. That's easy because it's the base case. We know what a width 1 triangle, what its width is. It's 1. And so we're going to make a special case out of that. And so we're going to have a method in our triangle class called getArea. And that'll be the method that the user of our class calls when they want to find the answer to what the area is of a triangle that they've already called the constructor on. Well, if the width that they initialize the class with is 1, when they call getArea, we will see that by reading the instance variable. We will see that the width is 1, and we will return 1. This, again, is our base case. Move right. That's not the case in general, though. And in order to solve the general case, what we're going to need to know is we're going to solve it in a process called induction. Mathematically, it would be called induction. And what we're going to assume is we're going to assume that we know the answer to the triangle, what the triangle number is of a triangle that has a width 1 smaller than the one we're currently working with. And so if we knew what the smaller area was, and we had a user call the getArea method on the current triangle, and we wanted to write the code that was going to answer that, we could say, oh, well, it's pretty easy if we know the smaller area, the area of a triangle that's width 1 smaller, we just take that smaller area and we add it to the width, or the number of blocks that are underneath that smaller triangle. And just by adding those two numbers together, we get the area of the total triangle. It consists of the smaller triangle and the baseline. So we can do that. We can create code that does that process, that algorithm, as follows. Within the getArea method, what we'll do is we'll create another triangle object. Now this is inside the existing triangle class. So within the triangle class, we're creating another triangle class, another instance of a triangle object. But the triangle object that we create when getArea is called is going to have a width that's 1 smaller than the width that we actually care about. But we want that because we're trying to figure out the area of the smaller triangle. So if we construct a triangle with a width 1 smaller, then we can just ask that smaller triangle, hey, tell me what your area is. This is like assuming we know the answer to the smaller part of the problem. We save that in a variable called smaller area. Move right. So the full method can look something like this. When someone calls our triangle object asking for the area of the triangle, area based on the number that was passed in when the constructor was called, we look and we see what the width is. And if the width that the user constructed us with was 1, then we return 1. Easy. If it's anything else, we construct a smaller triangle that has a width of 1 less, and we call the method getArea on that smaller triangle in order to return the area of our current triangle. And so we return the smaller area plus the current width. And in that way, we return the answer to our user's question of what the area is. Now this causes a recursive chain of calls, where each time a triangle is created, and another triangle is created, and another triangle is created, but each time another triangle is created, it's getting smaller by 1, and minus 1, and minus 1. And so the width is dropping with each recursive call until we get to a triangle that has width 1, and that triangle doesn't make any more calls. It just returns 1. And then we can back out of this chain of calls that we got until we got to the very first call, and now we know what the smaller area is, and we can add the current width to it. Move right. So for example, let's say we want to compute the area of a triangle with width of 4. Well, we're going to first call the constructor. We're going to create a new triangle. We're going to pass in the value of 4. Then on the object that's returned from the constructor, we're going to call the getArea method. When we go into the getArea method is going to say, hey, this isn't a width 1 triangle. So what we're going to need to do is we're going to need to make a smaller triangle that has a width of 3. And we're going to have to call getArea on that triangle. Well, that triangle is going to make a smaller triangle of width 2, and then call getArea on that triangle. And that triangle is going to make a smaller triangle of width 1, and call the getArea on that triangle. And that triangle sees that it's width 1, and returns 1. Well, so the triangle that was of width 2 says, the smaller triangle has an area of 1, I am width 2, so now my new area is 3. And I will return that because someone asked me what my area was. Well, it turns out that that was the triangle whose base was 3. And so that smaller area is now 3, and we add the current width 3 to it, and we get 6. So we return 6 to whoever called our getArea method on our triangle of width 3. Well, who called that? The triangle of width 4. And so we take our smaller area, 6, we add our current width to it, 4, and we end up with the value of 10. So we end up making one recursive call for, we call get area on a triangle 4, on a triangle 3, on a triangle 2, and a triangle of 1, making a total of 4 calls to the get area method. Move right. So generally speaking, what recursion is it's a computation that solves a problem by using the solution to a smaller problem. And there are basically two things that have to happen in order for a recursive solution to work. Every time you recursively call some method, you have to call it with a slightly smaller, a slightly simpler, a slightly version of the problem that's closer to your base case. Otherwise, you're never going to end the cycle of recursive calls. And then finally, the other thing that has to be present for a recursion to be successful is that there has to be a base case. There has to be a point at which you stop calling those recursive computations as well. So the simplest case. So to be fully robust, we want to make sure that the base case of our triangle example also can handle negative numbers. And so we'll also say if our width is less than or equal to 0, we'll return 0. So actually in that way we end up just with one base case of 0, because if we recursively call this with the width of 1, it'll still work. Move right. Now of course, recursive calls aren't the only way to solve this problem. We know that generally speaking, the area of a triangle is a sum. It's a sequence, a series sum. 1, 2, 3, all the way up to width. And so we could very easily just use a loop to solve this problem as well, where we initialize a loop with some area 0, and then we step through from 1 until the width of our triangle, including the width of our triangle. Notice that less than or equal. And each time through our loop, we increment our area by the next layer of bricks as we go on down our triangle. So that would be an iterative solution instead of a recursive solution. And then finally, there's a closed form solution, or a mathematical solution, which is determined from a formula based on the series. And when we have a series like this, we know that the area is equal to the width that we're looking for times the width plus 1 over 2. So it's a closed form solution. And in this case, of course, the most efficient thing to do would be to use math, because regardless of what width we call our triangle, regardless of the width of the triangle whose area we care about, it's always going to be a constant amount of work. Whereas the loop is going to be order n, where n is the width of our triangle, and the same with the recursive call as well. We can't always find a closed form mathematical solution to problems we care about. So let's stop there for a basic introduction to recursion and let you have a chance to reflect and think a little bit about the process of calculating triangle numbers. Thank you.